So this video is going to be about the experimental design, and it's going to be a review for the test that's coming up in a couple of days. Your job is to make sure you take notes and you study for it. This one tends to be a pretty tough one, so make sure you study for this one. So a scientific question. If you go back, we've studied what a scientific question is. It's much more than just a plain old question. Is the sky blue? There are certain factors that you need to think about when you create a question, and one of them is a cause and effect. So is there a cause and effect? Are there conditions you're testing and then something you're measuring because of those conditions? So there needs to be a cause and effect. It requires a test or an experiment. Okay, a test or an experiment. It is measurable. A lot of us still have a problem with general words. Look, cause and effect is on there twice because it's so important. We want to make sure it's measurable. Plant growth is not measurable. It's not specific enough. Plant height is measurable. It should not be a yes or no answer. No one-word answers, no opinion words. Okay, so measurable is really key, cause and effect. So take a minute, pause here if you need to, elaborate on what cause and effect is. Don't just write cause and effect. Don't just write measurable. Make sure you understand what that is. When it says requires a test or an experiment, don't just write that down. Make sure you understand it. Just because you've written it down doesn't mean it's transferring into your brain and you're remembering it. Okay, so jot a couple of these notes down. Now, take a pause for a moment, and on your notes page, I need you to create an example of a good scientific question, and then create an example of a poor scientific question. I want to see if you can actually use all of these ideas, cause and effect, test, measurable, no one-word answers, no opinion words, not a yes or no. I want to see if you can demonstrate that you know what a good scientific question looks like and that you can identify or create a bad scientific question. So pause here, make sure you understand about scientific questions. All right, next up is a hypothesis. A lot of you, when we first started talking about hypothesis, you said an educated guess. A lot of you said a prediction. In science, it is all of that, but it's also very much more specific. I actually want you to write it in the form of if, then, because. So if you're going to talk about your independent variable, your causes, the conditions you're testing. If I test hot water and cold water to see which one evaporates more, then I think the hot water is going to evaporate more because, so the if part is going to talk about your independent variable. The then part is going to talk about your dependent variable. The because part actually needs to explain why you think the way you think based on your research. Okay? Some of us are still struggling with the if, then, because. You're switching the cause and effect, and then your because isn't really an explanation, it's just a statement. So I need you to pause here for a moment, make sure you've got your notes, and actually create an example of a good hypothesis, and then in your notes create an example of a poor hypothesis. I want to see, can you demonstrate the if, then, because? Can you make sure that you write if, and then you talk about the conditions that you're testing, then you talk about what you're measuring, and because you give me a sound explanation, a scientific explanation. So pause here and make sure the notes are done and the examples are finished for your hypothesis. All right, so then let's pause here for a moment and talk about the actual design. An independent variable, another name for it is, I, oh, why am I drawing a blank? Independent variable. This is the conditions you're testing. So like hot water, cold water, heating lamp, no heating lamp, salt water, plain water. Um, what else did people test? All kinds of things. Dependent variable is what you're measuring. So this is how tall a plant grow, how much rain, precipitation you collected, um, how much evaporation happened. That's what you're actually going to measure. It's got to be measurable. You need to use a tool of some kind to measure it. Constant variables. Constants are things you hold the same. So, I'm using the same amount of water. I'm putting the containers in the same place. I'm using the same type of plant. I'm using the same types of bags. The more constants you have, the better your experiment's going to be. The only thing that changes should be the independent variable, should be the condition you're testing. Everything else should stay the same. Okay. Experimental groups. This is the group that is subjected to your test condition that's not a normal condition. The control group is the group that is experiencing the normal condition. Not all experiments will have an experimental group and a control group. And trials, we've talked about trials before, and I know you know this. The more trials you have, the more valid your experiment. When we actually ran our experiments, some groups got their experiments, they could run multiple trials in a day, and then since they did it for 2 days, some of them had 6, 12 trials. Some of you ran a trial for 24 hours, so you were only able to get 2, maybe 3 trials overall. So the more trials, the more valid your results are going to be. And that's just because any outliers, any whoopses, would all be averaged out mathematically. So some of us are still having an issue with the independent variable and the dependent variable. The independent variable is the variable that you are manipulating. The dependent variable is the responding variable, what happens because of the condition. List of materials. We still had a couple people have a problem with this. This is a bulleted list. See that little circle? That is a bullet. So it needs to be a bulleted list. It needs to include the quantities and the amounts, and these need to be the quantities and the amounts that you actually used. So some of us didn't use bullets. Some of us did not put quantities and amounts. And some of us didn't change the list of materials to what we actually used during the experiment. So this is all really important. So real scientists take this written report and share it with other scientists with the expectation that they can use the exact materials and they can follow your procedure exactly and come up with your exact results. In the real world of science, if that doesn't happen, then you have not created a valid experiment and your results are not valid. So if you watch the news, we are going through COVID. We're trying to get a vaccine. And all of these manufacturers needed to go through a whole bunch of steps prior to even creating the vaccine. And when they created this vaccine, they didn't just say, oh, we're going to test 10 people here in the United States, in Ohio. They tested people in different countries and different states, of people of different ages and ethnicities. And they made sure that the procedure they used in Ohio was the same they used in England and was the same they used in China. And if it wasn't, then they can't validate their results. And the CDC is going to throw out their results and say, try again. So it's really important that your list of materials and your procedure when you're doing science is the actual stuff and how to, so that somebody can replicate it and get your same results. So procedure, a numbered list. So instead of hitting the dot, you're going to hit the numbers up there and it'll number it automatically. And this should be exactly what you did and how you did it. And you need to put things in order and you need to make it detailed. Data tables. For the most part, we did pretty good. Spelling capitalization of headings. So amount of light capitalized after week 1, after week 2, after week 3, average height centimeters, full sun, shade, all capitalized, all bolded. Average. Some of you in that column just put average, and I said, average what? I need you to tell me what it's the average of and include units. Okay? You need to make sure you have a border drawn and that the text is centered. It just makes it easier to read. When scientists create their reports and then write up their articles and submit them to put into magazines, they're not fancy dancy. They're not super creative. There are certain ways they have to submit things because they're more interested in the actual science of it than pretty fonts and pretty colors. Okay, so data table. Graphs. So we did graphs, and I think for a lot of you, this was the first time on Google Sheets. So we had a 3-day lesson on it. So once you have your data tables, then we highlight specific things, and I taught you how to highlight different things to create these graphs. You need to have descriptive titles. Some of you gave me 1-word answers. Somebody gave me 2 words. If I look at the first graph, average plant height versus amount of light, then I'm going to assume that one of the axes is going to talk about plant height and the other one is going to talk about the amount of sunlight. And lo and behold, if I look, my x-axis says sunlight condition and my y-axis talks about plant height. So the graph's title is very explicit to what I'm looking at. Okay, notice on the y-axis, average plant height, I have centimeters in parentheses. Then if you look at the other graph, this one doesn't say average, it just says amount of sunlight versus plant height. Basically the same title, except for the average one, I put the word average in the front of it. The y-axis are both basically the same thing, except on the average graph, I put the word average in front of it. Now the x-axis is different. The x-axis is about the time. I wanted to see the first trial, the second trial, the third trial, the fourth trial, and I wanted to be able to see comparatively the sun versus the shade next to each other so that I could say, oh, after the first week, there wasn't any growth in the shade, but there was a lot of growth in the full sun. After the second week, there wasn't a lot of growth in the shade, but there was a lot. So it's very explicit, the information that I can gain from that graph. Okay, you have to be able to read graphs. You're going to have to do that in your state standardized tests. So we need to be able to make sure that we can create them and that we can read them. Okay, so graphs, very important. We'll do it from time to time. Conclusion. So some of us had some issues. You left my text in the written report. The written text that I wrote was a guide, and that was my expectations for each of those sections. And you weren't supposed to highlight your text. You were supposed to highlight my text. And as you highlight it with your cursor, with your mouse, then you start typing, it types over my text. So a conclusion is a paragraph, and some of you didn't write it as a paragraph. And paragraphs, when you write in English language arts, spelling, punctuation, capitalization, it all counts. It's all important. So when you write your paragraph, the first sentence, you're going to restate your purpose. And when you do that, you're going to include your independent variable and your dependent variable. Usually that's a sentence. You might take 2. What are your major findings? one or two sentence. The major findings we found in our experiment were the next sentence was your hypothesis supported by the data? My hypothesis, comma, da, 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 was supported by the data or was not supported by the data. The next sentence or two, what were your errors and how could this experiment be improved? I got to tell you, we all make errors. We are not professional scientists. So we are all going to make errors. So if your results aren't what you expected them to be, then maybe there was some kind of mistake. Maybe a certain procedure should have been done differently. And then the last sentence or two in your conclusion is what could be studied next after this experiment? What new experiment could continue study of this topic? So this is a paragraph. In essence, I should be able to read this paragraph and understand what your question was, what your hypothesis was, what your independent, dependent variables were. I should have a snapshot of what your data was, because that's your findings, and what possible mistakes were. So if I read your conclusion, I should get a really good grasp of what you did and what you learned from it. So this is experimental design. These are the parts of it. My expectation is that you know the requirements and the criteria for these, and that you be able to give me examples, good examples of these, or poor examples of these. Or if I give you examples, you can tell me, yep, this is a good one because it has this, this, and this, or this is a bad one because it's missing this, this, and this. So this test is a pretty challenging one because not only do you need to know about all these pieces and parts, but you need to be able to identify good ones and bad ones or poor ones and tell me why it's good or tell me why it's poor. So today, notes. Tomorrow, I'm going to give you some examples and we're going to start mirroring some of the test questions. Maybe you're going to make some flashcards to help you remember the criteria.